Today we need this file out of the regression data. The perch and brim weight, length, height, width. And this data is from Turkey, and we're on the perch page. The label at the bottom, and these may or may not be what you think of as perch, but they're shaped the same way anyway. Okay, we were doing simple linear regression, 1x, 1y. Right, in here, if we have weight as y, and this is in grams, the x variable can be a single thing or a combination of things. And we've got length, width, that's how long they are, the width, how fat through the center they are, and the height, top to bottom. The usual one that's done is the length, the weight and the length. If you go to the brim, these look like not a bluegill or a crappie or something like you might have seen, but it has the same shape. It's kind of flat, about standard top to bottom, looks more like a stretched out frisbee. A perch is more like a dolphin shape. If you look at the brim and graph, make a scatter plot of weight by total length. We want weight to be y and length to be x. And since the x and the y are in the wrong order, we have to do them individually. So we can add the x values first, which is the total length for these fish. And then the y values, which is the weight. Does it look like we can predict weight from length with a simple linear regression? Just length. Can we put a straight line through those points? Do the add trend line. And we don't need the equation necessarily, but we need the r squared. I put the equation on there too. Does it look like the straight line fits? It's got an r square of 0.89, 90% of the variation with weight is associated with length. Everything looks good. Go back to the perch, and we want the same kind of scatter plot of weight with length. So for this, select data, add the series. The x values are going to be length, and the y values are weight. So what do we get here? Does it look like a straight line? It's not as straight as the other one. If we put a line through it, it's going to be low on both ends, the top and the bottom, and high in the middle. Right? So this doesn't work as well. In this, these fish are shaped more like dolphins. They're long, they got a width, they got a height, and the longer the fish is, the more high it is, the more wide it is. So in these things, the dimensionality becomes important. I have a box. It's got a length, a width, and a height. And the volume of the box is equal to the length times the width times the height. And if I add density to it, I get the weight of that box. So that this is something engineers are more concerned about. But the units have to be associated. They have to match in some way. We have weight here, and we have volume on length, width times height. So if we have a measure of the specific gravity or something like that, how heavy it is, then we have a relation between these where this is cubic and this is cubic. If I do weight and length only, I have a three-dimensional weight compared to a one-dimensional length, and the units don't match. So one way that these things have to work sometimes is that we have to match the units, or at least get them going the same direction. So back to the perch. This is weight and length. We need weight and what's first? Weight and height. Make a scatter diagram for weight and height. So we need a scatter plot for weight by height. And since they're in the wrong order and they're separated, we've got to do it a different way, or at least do it individually. Select data, add. This is going to be weight and height, top to bottom size. So the x values is the height, top to bottom, and the y values are the weight. And we actually get a graph that looks very much like the one we had. It's not got a good linear relation in it. And if we do the same thing for length, or for width, thickness through the center, and total length, total weight, make a scatter diagram for weight and width. Weight and width. The x values are width hope I get it right here. Got in the way of my data. And weight. And basically, I get another one of the same thing I had. It's got a curve in it. The fix for this is to match the dimensions, so that rather than length, width, or height individually, I want the product of length, width, and height. I want the volume of the fish. So this is length times the height times the width. There's the length, that's the x's. Series x values, and the weight is the series y values. So we got it right. And there is the relation between weight and volume. So that I got a simple linear regression, but the x variable is a combination of other things. And now I've got something I can use for the regression. And here the r square is almost 1, which is what you should get from a relation like this, with a fish length, weight, and thickness, all the different things. Right? And again, this is, if we're doing fish or trees or snails or salamanders or whatever, you're going to get r square, or correlations that are extremely high. This correlation is basically 0.999. If you're doing with people or with economics or sociology or something like that, it's going to be an r, or r square, of 0.3. This works out. I've got one y and one x, and the x is length, width, and height, the volume of the fish. There is another kind of way to do this. And this is called a multiple regression. It's multiple linear regression. We have 3 variables now. Instead of just 1, we have 3 in this case. And we can have as many as we want. That makes it a multiple regression. It's exactly the same as the simple linear regression, except we can't plot it in 4 dimensions. All we can do is get what we had before individually. So you can't see these things like you can for a simple linear regression. And for this, we're going to use those 3 variables, length, height, and width, individually. And this is something you'll never have to do. It's no more difficult than the simple linear regression. But it's another way to get all of those variables together so that each one has its own slope. It has one intercept, the b0, and there's a slope for each one of the variables. So this will be the slope for the length, the height, and for the width. So it's the same kind of prediction as before. The way you have to do this in Excel is we have to use the data analysis toolpack regression. So if data analysis doesn't show up when you go to the data tab, we need to get the data analysis toolpack. All right, then we want to go to regression. And this has a particular setup that's the way Excel does it. But we go to regression, and we're going to input the Y range, the weight, just like before. Click on that box. We want to input Y, and that's just the regression for weight. That's the y variable. Oh, excuse me. Let me go back and redo that. We want the names here. We want the units. Crash out of that. Cancel that one. Go to the first line where it says perch. Right click on that where you got the line, the arrow showing, and insert. We want to put a new line in there. And here we're going to put the variable name. When we have multiple variables, we have to do it in order, or we need to put a name on it so we can figure out which one's which. Length, height, and it doesn't matter. All we need to do is be able to tell them apart. So when I mark the data, I'm going to mark the name as well as the numbers. So back to data, data analysis, and regression. Then for the y range, we want to start with the name and then mark the numbers. And we're going to include labels. Click on labels in that box, and that will put the names that we put in there onto the table of results. Then the X range has to be all of the X values. So you have to get all of them. And the way this is set up, all the X's have to be next to each other so you can include them all at once. So you go to the very start and block off all of those three columns, including the names and the numbers. Then the output range, just wherever we got a place to put it. So we've got the input range, the Y, is all of the weight, including the title, and the X is all of those three columns, including the titles. And we have labels checked so that it knows that those names are in there. Click OK. And this is the regression results for the analysis. Multiple linear regression. Come on, get out of the way. And the equation has an intercept of minus 510. The slope for the length, the multiplier times the length, is 3.88. The multiplier for the height is 72.7, and the multiplier for the width. So it's minus 510 plus 3.88 times the length, plus 72.8 times the height, plus 37.2 for the width, all multiplied individually and then added together. So there's 3 slope values and 1 intercept. If you look here at the t statistics, which ones have a t value that is outside of 2 or minus 2? If it's outside of 2, it's bigger than 2, and it's smaller than minus 2, then it's significant at the 95% level. That's the 95% between 2 and minus 2. The only one that does that is the height. The others aren't particularly significant, but they make the line straight. Up here, this is the F value. This is the significance of the regression, and it's basically a t-value squared. So anything bigger than 4 makes a significant prediction, significant regression. This one is 168. So it's a good regression. It's reliable regression, and the p-value, the actual significance level of the F statistic, is basically 0. We're so far out on the end that there's no space left. So that this makes all of the individual variables together. Each is a slope times its individual variable plus the intercept. So instead of one slope, one intercept, we have one intercept and 3 slopes, one for each one of the variables. That's a multiple linear regression. And it's no more difficult to do than the simple linear regression, but there is no way to look at it all together. You can't make a scatter plot in more than 3 dimensions, basically. You can make a 3-dimensional scatter plot, not in Excel, but there's other packages that will do it. But that's another way to do this regression, rather than length times width times height. I put in length individually, height individually, and width individually, and make it a multiple linear regression. And it works pretty much as well as the length times the width times the height. All right, this is common for things like hospital expenditures. How many people in the family? Where do you live? How far do you live from a hospital? All of those things go into hospital expenditures. This is how they cite McDonald's. What's the population density around the proposed location? That can be X1. What's the number of other fast food places within a certain distance? That becomes number 2. Number 3 can be, what is the state of the roads that get you there? How many turns do you have to make? How many different places do you have to stop or go? This is what makes up traffic lights, the timing on traffic lights. X1 can be how many cars in the line in this lane. X2 is how many in the next lane. X3 is that lane. X4 is that lane. X5 is it 4 lane or 2 lane? On and on and on and on. This is very common for insurance rates. What kind of car you've got? What's your driving record? How many accidents have you had? What's the prevalence of accidents in your area?